সো এই ট্রান্সফারে ফোর্স কনভেকশনের কাজ হবে। প্রথমে আমরা করছি হচ্ছে ইয়েতে এক্সটার্নাল ফ্লোতে কাজে করাবো, সেটা হচ্ছে দেখ মেইন থিং আমি সেগুলো হচ্ছে এখানে ডিসকাস করবো। রেস্ট অফ দ্য থিং আই উইল লিভ। ফ্রিকশন ডেভেলপ কীভাবে হচ্ছে বা কীভাবে সব হচ্ছে সেটা দেখিয়ে দিবি। টাউ ইকুয়াল টু CF বাই 2 ইন্টু রো ইন্টু ইনফিনিটি স্কোয়ার। ওকে, laminar flow delta is 5 by root over REX, or CF value is 0.664 into root over REX. Okay, laminar flow is the ratio of inertial force upon discussed course. Okay, you know, and here there is a width and there is a length, there is a change, and the main value that is under 5 into 10 to the power 5, that is laminar flow, and greater than 5 into 10 to the power 5, that is turbulent flow. Okay, that you need to see. Now how cooling is that? Is T infinity, that is cold fluid, and T infinity is greater and Ts is lower, so Ts is greater, so cold fluid over hot fluid. So it is the fluid is cold because T is the temperature and alpha is the plate outside temperature, and T infinity is the fluid temperature that is greater than this. So hot fluid is flowing over, T infinity is the outside temperature, so a fluid now, so T infinity it is greater. Okay, now 90 minus Ts by Ts minus T infinity, these things. So this is main point. It is the boundary condition. There is a convection and conduction, those two values are same, and here it is saying that if this x value is greater, then dy by dt is decreasing, q value is also decreasing, h value is also decreasing. So that's why how is proportional thermal boundary increases with heat flux decreases. Good Prandtl number. Then second is Prandtl number, that is the ratio of mu Cp by K fluid. Okay, how is coming? That's the dimensional numbers, that is the momentum diffusion by thermal diffusion. Now সবাইকে তেল লাগাতে লাগে, তাই জন্য air is greater than 1, momentum diffusion is greater. For liquid it is less than 1, or gases air is almost 1. These are the, and it is this. And for laminar flow, delta by delta T is that the laminar मतलब delta by delta मतलब this is thermal and this is hydraulic. Terminal flow rapid mixing, so no importance this role কোনো play করে না. Nusselt number, this is the ratio. This is the main thing that you need to see. There are many questions, then the nuances that you need to catch up, and from those things the question will be. That is the HLC by cube, everyone will know, but the characteristic length, how is the length is varying, how is the flow is boundaries developing, what is theta star, these are the things that is small things that really vary. So Q convection by Q conduction, and same thing you have also read in Barrett number also. So these are the ratio of Q convection by air. So when moving, the carries the double energy. Okay, this is saying Nusselt number is this thing, convection is this thing. So Nusselt number and boundary condition, those are the two things that are same that have been said. And Nusselt number is a function of Reynolds number and Prandtl number. These things I have said. Nusselt number is there is a relation, no? So Reynolds energy or Sternberg energy. So here these are the U infinity and U, matlab thermal and hydraulic, these are almost same. Now tau equal to CF into rho U infinity square by 2, CF into rho U infinity square by 2. These are the things you need to see. And H by U infinity is equal to CF by 2. Okay, U by U infinity equal to CP equal to standard number. Standard number is CF by 2, that you need to see. Standard number is how it's coming. Q convection is thermal energy of the fluid, convection by thermal energy. So H by rho U infinity into Cp, standard number. That is, so you can see that is Nusselt number by Reynolds number into Prandtl number. You can also see these are the things that are really not needed for this thing. Now boundary condition, there is a two boundary condition, that when temperature is constant and its heat flux is constant. Okay, so it's constant Ts minus T infinity, temperature is constant, fast condition. There is a rigid boundary condition that we have seen there, and that is that H bar is 1 by A 0 to U HA into dA. So these things that you are not remembering, these things that you need to really take care of. And now x equal to 0 to x equal to L. So how it is differentiating, it will put x into 0 per assume. So x h bar 2 h equal to x equal to L, that is 1.1 time. Okay, Q equal to H8, it is exam question come. And heat flux, amount of heat transfer per unit area, you know. Then Newman's but that is d sheet, that is temperature constant, and the Newman heat transfer condition, there is the heat flux is constant, the heat flux value that is constant, and Q equal to Q into A. These things I am not going to say you. The thing with test or correlation used in force convection. So what is the, this a flat plate surface are maintained in constant temperature. So delta is 5 by Rex for laminar flow, 0.664 by root over Rex. You can also say root over. So CF equal to convection, CF equal to, that is the value. Now these are the when surface maintenance temperature that is constant, then h equal to x to the power minus or 1 by root over x. This is the value, and Nusselt number value is 0.332 into re to the power 1 by 2 and pa to the power 1 by 3, and produces these things. And then the final things is that the h bar is 2 into h bar at L. Nusselt number is nu into to the power x, and it is 1 by root 2. Now laminar flow case is Nusselt number 0.45 into RT to the power 1 by 2, Prandtl number to the power 1 by 3. So Nusselt number is 1.5 time here, it is 1.5 time, H bar also 1.5. And previous cases we have seen when that was laminar case, there that was 2 times, but in case it is so these things we have seen. Then delta by delta t, you also seen this. Now Nusselt number, this is thing. The thing is, for all equation this is valid, that is Kohlberg's analogy valid for any fluid, that is standard number is equal to Prandtl number to the power 2 by 3 into skin fraction by 2. Now standard number that you can see, standard number, student, that you can see standard number is CF by 2. Also CF we can also see, right student, like 0.644 by root over area. So it's a small value. Then we are coming to a turbulent flow over a flat plate. Here the surface maintain is constant temperature, and what are the values? This is conferences. So this is that directly the value that we need to see is that hx is proportional to x to the power minus 1 by 5. What value? X to the power minus 1 by 5. Okay, and if you come back, then you can also see the h bar. So h bar is 5 by 4 into hx to the power L, so it's 5 bar. So nu equal to h bar into hl by k, or 5 by 4 to nu x, so 1.25, it is 1.25 time. Okay, turbulent flow surface maintenance constant heat flux condition we are getting. So that is 0.3608. it is not coming that very as compared to previous, very low, it is very low, it's not coming. There is only 4% heat flux condition, that is 4% higher than this thing. And then the temperature variation, how it's flowing, that is being shown. So I am not going to see. Then come to the part where it is internal flow, force convection internal flow. This part we are saying. So it's internal flow. So the first is hydraulic perimeter. So this is the Reynolds number perimeter, that is 4AC by P, 4AC by perimeter. This is hydraulic diameter. Duct is not circular, and it is previously pressure no low pressure difference, and circular pipe there is a high pressure difference. So duct is 40 AC, this is 40 by 4, that is D for circular thing, and for rectangle it is area, and for hydraulic it is 2 AB by A plus B. Okay, you can see. And each thing is different, 4 by pi by 4 di into dy into di by plus d2. Real number is 4 m dot, that mass flow rate by rho d into mu. So 4 and so rho v, so rho v you can see 4 m dot by rho d pi d into mu, pi d by mu, 4 m dot by pi d by mu. We can also write this as Reynolds number we can see is that 4 m dot by pi d into mu. So generally this value is Nusselt number is hd by kh, hydraulic length, how is developing region, changing velocity, these are the things. How is pressure velocity difference, and how shear stress is changing, that you can see. Fully regular laminar flow rate, and this is the mean profile. And these things are some question come, equal to 2 by r square, 0 to r u into rx to into r. So how is coming? M dot equal to ideal to m dot actual. So m rho into um dot square, that is from there equal to 2 r square into r. It is very important. And so fluid, so thermal boundary layer temperature is a vector, and cannot use arrow. Temperature is a vector, so it is a cannot use any arrow, so that's why there is no arrow that has been put in here. So distance from start to the merge point, that is the point, and the H value is kilojoule per kg, we can see. So it is Q convection HST and conduction HST into TS. So for interview, these things are dimensional profile. So it is the profile, how is changing, how is going down. So these values that you can see, H by K is constant always. What is written here, you just pause and see. Now entry length is that, how is the entry length for laminar flow, it is 0.05 into RE into dr. So Prandtl number is LT, that is thermal entry length by hydrodynamic. So thermal by hydrodynamic entry length. So for gas, what is happening? For gas, what is happening? These are equal, and for oil, thermal entry length is more than hydrodynamic, and for liquid, thermal entry length is less than, and hydraulic is more. For liquid, hydraulic is more. For oil, temperature is more. Okay, there's one more thing, there's a golden rule that has been written. and then I am not gonna see this. So when is the constant maintained constant temperature, what is the value that is coming? Tm minus ts. So tm minus ts, this value by ti minus ts. So first value ti by ts is e to the power hpl by mc, hpl by hpx by m dot c. So hpx by m dot c, that is the NTU value. Okay, so hpx minus NTU. So NTU generally varies till 5. So it's varies with increasing the length. So now LMTD lower mean temperature. So I have said that delta T1, this is delta T1 minus delta T2 by delta T1 by delta T2. How is getting that you can see. And the bulk is Ti plus To by 2. MTD for linear profile, for that reason why LMTD is used. MTD is suitable for only linear profiles, so MTD is linear. For that reason here LMTD is using. Then these are the important point. When surface is maintained as constant heat flux, then what will I get? So it is a constant heat flux, this is the value, this temperature. So gate question will come from here. So dt by dx equal constant, this is the constant, equal to h ts minus tm. So ts minus tm, ts tm, these are the two temperature, these are constant. Okay, just don't read, just try to go deeper. Laminar flow through pipe and surface maintain at constant temperature, that is for circular pipes. Real number is less than 2300, so it is 3.66 into k by d. So each k by d is equal to 3.66 on Nusselt number. Nusselt number is 3.66. Laminar flow through a pipe surface maintain at constant heat flux, that is RE less than 0.3. So H equal to 4.36 into K by D. So H equal to 4.36 of Nusselt number. And fully damped laminar constant heat flux gives 19% more than this value. H is proportional to 1 by D. So H2 equal to 2H. And Reynolds number is 4m by pi t into u. You have seen is turbulent flow through a pipe. This turbulence 0.023 and 2 equals 0.8 Prandtl number 2. So standard number and Prandtl number for turbulent 2 equal 3 equal to by 8. This is the value. So D's value keeps increasing. And how is this? Okay, I hope this is the end.